Hello friends, welcome to VK lectures. In this lecture we will be discussing about the analytical function from complex analysis. Now here we have the point. This is the complex number z, which is given by x plus iy, where this is the real coordinate and y is the imaginary coordinate. So x is the imaginary real part, y is the imaginary part. So we can write z is equal to x plus iy. Now if you consider in polar coordinates, where r is the radius, radius means the distance from the center to that point. So we can also write the complex number z as a function of theta. This is the angle theta. So z is equal to r e to the power I theta. And what is r? R is nothing but root of, this is y, this is x. So this is the hypotenuse, so it will be equal to x square plus y squared. Now in polar coordinates, as we have said, z is equal to r e to the power I theta. This term is called, or if you convert e to the power I theta equal to cos theta plus I sin theta. I sin theta, we can write z equal to r times cos theta plus I sin theta. Now this value is called principal value. Now when I start from here and I make a complete rotation to reaches the pi by 2, pi, 3 pi by 2, again to 2 pi, and then again back to this point. Let us write this point as a. Then I make a complete rotation, that means complete 2 pi rotation, which means z, I get the same point, z equal to e to the power I theta, r e to the power I theta. This is equal to r e to the power I theta plus 2 pi, or I can make any n number of rotations. So z is equal to r e to the power I theta plus 2n pi. So theta plus 2n pi, this term or z remains the same. Z, which is r e to the power I theta, this one remains same even after n rotations. So this term is called general value. General value. Okay. If you write it in terms of cos, it will be cos 2n pi plus I sin 2n pi. Please, there is a correction. This is z is equal to r times cos theta plus 2n pi plus I sin theta plus 2n pi. This is how you write the general value. Here we have the question: find the principal and general value for the following. First question is I to the power I. Now what is e to the power I theta? This is equal to cos theta plus I sin theta. Now I need I. If I need I, this sin theta should be equal to 1 and cos theta should be equal to 0. Now when theta equal to pi by 2, e to the power I pi by 2 equal to cos pi by 2 plus I sin pi by 2. So cos pi by 2 is 0 plus I sin pi by 2 is 1. So that's equal to I, which means e to the power I pi by 2 equal to I. Now we have got what is I. Now I to the power I, so first I we will replace it with e to the power I pi by 2. So e to the power I pi by 2 whole to the power I. This becomes e to the power I pi by 2 star, that means into I, that's equal to e to the power minus pi by 2. Now if you multiply by 2n pi, you will get the general value. So e to the power I pi by 2, you can take it like this, plus 2n pi. If you want to take pi by 2 outside, e to the power I pi by 2 into 1 plus 4n. So this is the general value, and here we have the principal value. So principal value, this is the general value. Now we coming to the second question, root I to the power root I. So root of I can be written as, we have already seen what is I, e to the power I pi by 2. So root I will be equal to e to the power I pi by 2 whole to the power 1 by 2. This gives us e to the power I pi by 4. Then so that's equal to e to the power I pi by 4 is cos of pi by 4 plus I sin pi by 4. So this becomes the root I, that's equal to 1 by cos pi by 2 is 1 by root 2. So 1 by root 2 plus I times 1 by root 2, that is I by root 2. Now this is root I. Now root I to the power root I. So e to the power I pi by 2, that is I pi by 4, that is root I to the power 1 by root 2 plus I by root 2. This is similar to writing e to the power I pi by 4 into e to the power 1 by root 2 plus sorry, that's not like that, e to the power I pi by 4 into 1 by root 2 into e to the power I pi by 4 into I by root 2. So the first term gives e to the power I pi by 4 root 2 into e to the power minus pi by 4 root 2. So this becomes the principal value. This can be converted into uh, cos of pi by 4 root 2 plus I sine of pi by 4 root 2. This term you can keep it like that, and for finding the general value, multiply by or add 2n pi to the angle, that is here pi by 4 root 2 plus 2n pi in both cosine sine. Here we are going to deal with the principal and the general value of z in logarithmic terms. That means we are going to find the principal value and general value for log z. Now we can write the complex number z in polar coordinates as r e to the power I theta, where that is also can be written as r into cos theta plus I sine theta. Okay. Now what is log z? Log z is equal to log of r e to the power I theta. So this can be written as log r plus log e to the power I theta. That's equal to log r plus log of e to the power I theta is nothing but I theta. Okay. Now we also know that if you rotate for 2n pi times, there is no change in log z. So log z is equal to log r plus log I theta. That also can be written as log r plus I comma theta plus 2n pi. So this is the principal value. Now here we have the general value. So log r plus, now this also can be written as log r plus I theta plus I 2n pi. Now this term is nothing but log z. So we can write the log this, let it be log z. So log z is equal to, this one is log z plus I times 2n pi. So this is the general value. This is principal value. So general value is equal to the principal value, that is this one, plus 2n pi I. Here are few trigonometric functions that are necessary for doing the problems in the next session. Please kindly make a note of it. E to the power z. So what is z equal to? Z is equal to x plus iy. So this gives us e to the power z, that is x plus iy. Now separate this. This is equal to e to the power x into e to the power iy. Okay. Now what is e to the power ix in general? That's equal to cos x plus I sin y. Now this is equal to e to the power x into e to the power iy is cos y plus I sin y. Now this is equal to e to the power x into cos y plus I into e to the power x into sin y. Now this gives us the real part. What is the real part here? E to the power x into cos y and the imaginary part is equal to e to the power x into sine y. E to the power z square. So we know the value of z, or z is equal to x plus iy. This we can write it as e to the power z square is equal to e to the power x plus iy squared. So that's equal to uh, e to the power x square minus y square plus 2x I y. This we can do e to the power x square minus y square into e to the power I 2x y. Now e to the power I 2x y, e to the power I theta equal to cos theta plus I sin theta. So this e to the power z square, e to the power z square can be written as e to the power x square minus y square into cos of 2xy plus I sin of 2xy. Now e to the power x square minus y square into cos of 2xy is the real part, and e to the power x square minus y square into sin of 2xy is the imaginary part. Now coming to sin z, here sin of x plus iy. To do this we must know sin of a plus b. Sin of a plus b is sin a cos b, sin a cos b plus cos a sin b. Now sin of x plus iy equal to sin of x into cos of iy plus cos of x into sin of iy. Now what we know, cos of iy equal to cos hyperbolic y, and the sin of iy equal to I sin hyperbolic y. Now replace this, so sin x into cos iy is cos hyperbolic y plus cos x into I sin hyperbolic, so I sin hyperbolic y. Now this becomes the real part, and this is the imaginary part. Here the analytical function f of z is given by u plus iv, and where u is function of x and y, that is the real part of the analytical function, and here we also have v, which is also a function of x and y, which is imaginary. Now for a function f of z to be analytical, here dou u by dou x should be equal to dou v by dou y, and dou u by dou y should be equal to minus dou v by dou x. This is the necessary condition, which is also called the Cauchy-Riemann conditions. The sufficient condition is that dou u by dou x, dou u by dou y, and dou v by dou x and dou v by dou y should be continuous, and it also must be the condition that it should also follow that f dash of z should exist. Okay, it should be a finite value. Check if the following functions are analytical or not. F of z equal to sin z. Now this can be written as sine of x plus iy, and we have already done that. This f of z is equal to sin x into cos hyperbolic y plus I into cos x times sin hyperbolic y. Now this f of z. Now even if you can write f of z equal to u plus iv, then u equal to sin x cos hyperbolic y and v equal to cos x sin hyperbolic y. Now we need to find out the dou u by dou x. So dou u by dou x is with respect to x. So sin x will become cos x. Cos x into cos hyperbolic y. Now dou u by dou y. So that is equal to sin x into cos hyperbolic y is sin hyperbolic y. Now we need dou v by dou x. Dou v is so minus sin x into sin hyperbolic y, and dou v by dou y equal to cos x into sin cos hyperbolic y. Now we need to check whether dou v, what is the condition? Cauchy-Riemann condition is, or necessary condition?
Dou u by dou x is equals to dou v by dou y.
Dou u by dou x equal to dou v by dou y, and dou v by dou x equal to minus dou u by dou y. Okay. So dou u by dou x, cos x into cos hyperbolic y, is equal to dou v by dou y. So look at this. This is 1, this is 2. 1 and 2 are the same. Now dou v by dou x, dou v by dou x is this, minus sin x into sin hyperbolic y. But this is equal to, but there is a minus sign. That is why here minus dou. So minus of sin hyperbolic. So equation 3 and equation 4 are minus of each other. Minus of each other. So this condition is satisfied. And we also have seen that all the first derivative, dou u by dou x, dou u by dou y, dou v by dou x, and dou u by dou y exist, which means f dash of z exists. So this is an analytical function. Please consider doing this problem as practice work. Here you have to consider z is equal to x plus iy, and f of z is equal to 1 by x plus iy. So dividing by a complex number is not possible, so what you have to do is multiply and divide by its complex conjugate, which will be equal to x minus iy divided by x minus iy. So in the denominator you will get x square plus y square, and in the numerator we have x minus iy. So u, the real part, is equal to x divided by x square plus y square. Similarly, the imaginary part v is equal to minus y divided by x square plus y square. So kindly find out the necessary conditions or Cauchy-Riemann condition, CR, and also find whether f dash of z exists or not. Here, thus, as we know, f of z is equal to u plus iv, and u of x comma y is the real part, while v of x comma y is the imaginary part. Now this both u as well as v obeys Laplace equation, that is dou square u by dou x square plus dou square u by dou y square equal to 0. That is del square u is 0, and similarly del square v is also equal to 0. Now this implies that u and v are harmonic conjugates, which again tells you that if you know u, we can find v, and if we know v, we can find u. They are orthogonal. Okay. So in the next application we are going to find how can we get u when v is given as well as v when u is given. Which of the following cannot be the real part of the analytical function? Any analytical function, which of the following cannot be the real part? So let's take the first one, u equal to xy square. So dou square u by dou x square is equal to 0. Dou square u by dou y square equal to 2yx, so 2x. Now del square u equal to sum of these two, that's equal to 0. Okay, now b, x square minus y square, u equal to, now dou square u by dou x square, dou square u by dou x square is 2x, that is 2, and dou square u by dou y square equal to minus 2. Here del square u equal to 0.
Excuse me, sir.
Yes. The option C, x cube minus 3xy square, that's u. Dou square u by dou x square. So first derivative will be 3x. Okay, let's do that. Dou by dou x of dou by dou x of u, that's dou by dou x of, that is 3x square minus 3y squared. So that's first derivative means 6x, because this is okay. Now dou square u by dou y square, that's equal to dou by dou y of u, that is dou by dou y of this becomes minus 6xy. this becomes minus 6x. So this gives us del square u equal to 0. Similarly, option D, 2 times, sorry, 2x times 1 minus y, you can separately write 2x minus 2xy, that's equal to u. So dou square u by dou x square. First derivative gives us 2 minus 2y, second derivative gives us 0. Dou square u by dou y square, first derivative gives us minus 2x, second derivative gives us 0. So this is also del square u equal to 0. So this C and D also can be the real part. Okay. So here f of xy is given. We have to find a. There is a in the both u and v. So find a if f of x comma y is analytical. Now u is equal to 1 plus x plus y into 1 plus x minus y plus a times x square minus y square minus 1. Now let's write, just rearrange this, 1 plus x plus y and 1 plus x minus y. So this is a plus b into a minus b. So a square minus b square, 1 plus x whole square minus y square plus a into x square minus y square minus 1. Now let's find dou u by dou x, which gives us 2 into 1 plus x, this term goes, plus a times x square derivative is 2x. Now just separate it, 2 plus 2x, 2 plus 2x plus 2ax. So that's the dou u by dou x. Now on the other side we have v, which is equal to 2y into 1 minus x minus ax. So dou v by dou y equal to, only one term is there, so 2 times 1 minus x minus ax, that's equal to 2 minus 2x minus 2ax. Okay, now dou u by dou x equal to dou v by dou y, which implies 2 plus 2x plus 2ax equal to 2 minus 2x minus 2ax. 2 gets cancelled, bring the 2x to the right side, 4x equal to, bring this to the other side, minus 4ax, x and x gets cancelled, a equal to minus 4 by 4 is minus 1. Application of analytical function. Now this f of z is equal to u plus I times v, where u is a function of x comma y plus I times the v of x comma y. So this is u, which is the real part of the complex number function, and v is the imaginary part. Now if f of z is analytic, we can write del square u is equal to 0, as well as del square v is equal to 0. They are called harmonic conjugates. This implies u and v are harmonic conjugates. Now, which means if we find u, you can find, if you get u, you can find v, and if you are given v, you can find u. Okay, so suppose we have u of x comma y, which is a given quantity. Then we can find v of x comma y. Similarly, if v of x comma y is given, then we can also find u of x comma y. Now the Cauchy-Riemann equation says that dou u by dou x equal to dou v by dou y, and dou v by dou x equal to minus dou u by dou y. Okay. Now this both are exact differentials. These both equations are exact differential equation. So let's take the case of the first one, that is finding v from u as given. So u of x comma y is given. So find v of x comma y. Now let's start with what is v of x comma y. V of x comma y can be written as, or dv of x comma y can be written as dou v by dou x into dx plus dou v by dou y into dy. This is just partially derivative. This is the dv, which is equal to dou v by dou x into dx plus dou v by dou y into dy. Now that's the thing. Now with the Cauchy-Riemann equation, we can substitute what is dou v by dou x. Dou v by dou x is minus dou u by dou y minus dou u by dou y times dx plus dou v by dou y. Dou v by dou y is dou u by dou x into dy. Now so v can be written as integral minus dou u by dou y into dx plus integral dou u by dou x into dy. Now this dou u by dou x, there is no x terms, there should not be any x terms, while for the first one y is considered as constant because you are integrating with respect to x. And in the dou u by dou x, if there is x terms, for example dou u by dou x gives you y plus x square, then you need to take only y from here. That is you have to subtract the x terms. No x terms should be here on the dou u by dou x term. Okay. Now the second one, v of xy is given. Xy is given and we have to find u of x comma y. We have to find the real part. Now what is real part u of x comma y? That's equal to dou u by dou x into dx plus dou u by dou y into dy. Then u of x comma y equal to integral dou u by dou x is nothing but dou v by dou y into dx plus dou u by dou y is minus dou v by dou x into dy. Now here the first term is y being constant because it is with respect to x, and in the second term there should be no x terms. In this integration there should be no x terms. So this yields us u of x comma y. Now let us write down the first and second equations. First one is regarding v of x comma y is the imaginary part is equal to minus integral dou u by dou y into dx plus integral dou u by dou x into dy. Now this means no x terms here. Here y is constant because you are integrating with respect to x. Similarly, u of x comma y is equal to integral dou v by dou y into dx minus integral dou v by dou y, dou v by dou x into dy, and here also there should not be no x terms. Yeah, we have a question from the analytical function application. V of xy is what we are asked to find and u of xy is what is given, and this is the formula. V of xy equal to integral minus dou u by dou y into dx plus dou u by dou x into dy. Now here we have u equal to x plus half times x square minus y squared dou u by dou x. Let's find dou u by dou x, that's equal to 1 plus 2x, and dou u by dou y is equal to minus y. Now from dou u by dou x, it should not contain x terms, so you can remove 2x from here. Then this is not 2x, 1 plus 2x by 2, so it's 1 plus x. So you can remove x term from here, and dou u by dou y equal to minus y, and here minus y is a constant. So now putting in the equation, v of x comma y equal to minus integral dou u by dou y. Dou u by dou y is minus y dx plus integral dou u by dou x is 1 dy. y. So that's equal to y dx is xy, dy integral is y. So that's equal to y plus xy, which is equal to v of x comma y. Now here what you can find is I have given v of x comma y is equal to y plus xy. That is, question is v is equal to y plus xy. Find uh, u of x comma y. Number 2, u of x comma y is given as x square minus y square minus 2xy minus 2x plus 3y. So let's find dou u by dou x. That's equal to 2x 0 minus 2y minus 2, and dou u by dou y is equal to minus 2y minus 2x and plus 3. Now from dou u by dou x, so what is the formula? Formula is integral dou u by dou y into dx plus integral dou u by dou x into dy. Dou u by, this is dou u by dou y with a minus sign, and this should not contain any x terms, so that gives us v of x comma y. Now that's minus integral dou u by dou y. Dou u by dou y is minus 2y minus 2y minus 2x plus 3 times dx plus integral dou u by dou x, the first term, so there should not be any x terms, so 2x can be removed, minus 2y minus 2 minus 2y minus 2 dy. So this gives us minus 2y integral with respect to x is 2xy, then again minus 2x with respect to x, that's x squared by 2, so plus x squared 3x minus 3x plus minus 2y, so minus y squared by 2 by into 2, that is minus y square minus 2y. So that gives us x squared minus y squared, so x square minus y square, now plus 2xy then minus 3x minus 2y. So this is v of x comma y, and again v of x comma y is this. Find u of x comma y. The real part of the analytical function is u of xy is given as 2x into 1 minus y. The corresponding imaginary part is alpha x square plus beta y plus gamma times y square. So we have to find what is alpha, beta and gamma. So directly is the question that u given, we have to find v. So let's start with dou u by dou x, that's equal to 2 times 1 minus y, that's equal to 2 minus 2y. Now dou u by dou y, that's equal to 2x into minus 1, that's minus 2x. Now the Cauchy Riemann says the first one, dou u by dou x is equal to dou v by dou y, that's equal to dou u by dou x. Now from here v is equal to, what is v, dou u by dou x integral dou u by dou x integral dy, that's equal to dou u by dou x is 2 minus 2y integral with respect to dy, that's equal to 2y minus y squared. Now the second one says dou u by dou y equal to minus dou v by dou x, which implies v is equal to minus integral dou u by dou y into dx, that's equal to integral, the minus sign, minus 2x with respect to dx, that's equal to x square. So u of x comma y equal to 2y minus y square, 2y minus y square, now that's plus x squared. Now we already have u of xy given in the question, which is equal to alpha times x square plus beta times beta times y plus gamma times y squared. So now what you have to do, compare the coefficients. Comparing coefficients of so alpha x square is, so alpha equal to 1, then beta y, so beta equal to 2, and gamma y square, so gamma equal to minus 1. Again, the question is to find u of xy, the real part, when the imaginary part is given. This is the formula here, and this should not contain x terms. Okay, so let us start with dou v by dou x, that's equal to minus cos x into sine y. So dou v by dou x already had a x term, so this need not be added. Now again, dou v by dou y is equal to minus sine x into sine y, differentiation is cos y. Now u of x comma y equal to integral dou v by dou y into dx minus integral dou v by dou x into dy. Now this term dou v by dou x is minus cos x into sine y, so it contains x term, so this is 0. Okay, this term is 0. You will only remain with the first term, that is integral dou v by dou y is minus sine x into cos y into dx. Sine x integral is minus cos x, so that's equal to minus of sine x integral minus cos x cos y, that's equal to cos x cos y. Here's a new concept, my Milne-Thomson method. Now this is to find f of z. We know that f of z is equal to u of x comma y plus I times v of x comma y. So far we have been dealing with u given, that is the real part is given, and we are asked to find out v, or v given, we are asked to find out u. Now one of this is given, or any combination, the addition or the subtraction of this is given, we have to find f of z. Now in general we can write f of z is equal to u plus I times v, which means I times f of z will be equal to iu minus v. Now let's add these two quantities. 1 plus 2 gives f of z into 1 plus I is equal to, on the right hand side we have u minus v plus I into u plus v. Now assume that f of z into 1 plus I is equal to, okay, now before that let us write down once again this one. So u minus v plus I into u plus v. Now let this be equal to f of z, this entire quantity, f of small letter f of z into 1 plus I, that's equal to, let this be u plus v, where f of z equal to 1 plus I into f of z, and capital U equal to u minus v, and capital V equal to u plus v. Now this is similar to our function f of z equal to u plus v. Instead of this, here we have capital F of z equal to capital U plus, so this is iv, here also I times v. Now from after finding out f of z, because u and v, if we can find u, you can get v. So through this, if you want to find f of z from either u minus v or u plus v or u or v, f of z is equal to capital F of z divided by, from this equation, 1 plus I. So if u of xy is given, u of x comma y is given, then f of z is equal to integral dou u by dou x at x equal to z and y equal to 0 times dz minus I into integral dou u by dou y at x equal to z and y equal to 0 into dz. Find f of z when u of x comma y is given, that is 2x plus y cube minus 3x square y. Now let's write down the formula. F of z equal to integral dou u by dou x at x equal to z and y equal to 0 times dz minus I into dou u by dou y at x equal to z and y equal to 0 dz. So let's find out what is dou u by dou x. Dou u by dou x is equal to 2 minus 6 6xy. 6xy. Now at x equal to z and y equal to 0, you get just 2. Now dou u by dou y is equal to minus 3y square, sorry, 3y square minus 3x square. Now at x equal to z and y equal to 0, you get minus 3x square minus 3z square. So now putting it in the equation, integral dou u by dou x at x equals to dou u by dou x, so that is 2 times dz minus I into integral dou u by dou y, that is minus 3z square minus 3z square dz, so that's equal to 2z plus I into 3z square is z cube by 3, so z cube. So 2z plus I z cube, this is equal to f of z. If you want the real part, u of z is equal to 2z and v of z is equal to z cube. So when v is given, how will you find out the f of z? The formula is integral dou v by dou y at x equal to z and y equal to 0 dz plus I into integral dou v by dou x at x equal to z and y equal to 0 dz. So the question is given, v of x comma y is equal to e to the power x into x cos y minus y sin y. Now let's start with dou v by dou x, that's e to the power x into x cos y. So cos y into e to the power x into derivative of x, that is e to the power x plus x into e to the power x. Now this one at x equal to z and y equal to 0 means we have cos y cos 0 is 1, so e to the power z plus z e to the power z. Now dou v by dou y equal to again we have e to the power x into x. Cos y differentiation is sin y with a minus sign minus sin y minus so let's e to the power x, differentiation of e to the power x into y sin y, differentiation of y sin y is y into differentiation of sin y is cos y plus differentiation of y with sin y. Now this one, the entire term at x equal to z and y equal to 0 implies you have the sin y terms, this term gets to 0, e to the power z, again that's the entire term give rise to 0. Now we have only dou v by dou x, so that is dou v, so I so integral I times integral dou v by dou x at x equal to z, that is e to the power z plus z e to the power z. Now z e to the power z 1 0, this is the first differentiation is 1, second differentiation is 0, integral e to the power z and again integral e to the power z. First term is plus, second term is minus, so it is z e to the power z 1 minus 1 times e to the power z is minus e to the power z. So this is dz gives us I into e to the power z is e to the power z, and second one z e to the power z minus e to the power z. These two are the same term with negative opposite sign, so f of z equal to I times z e to the power z. There is no real part for this v or f of z. Now the question is that u minus v is given. U minus v is in the sense the real part of the complex number f of z, which is equal to 1 plus I times f of z. This is what we need to remember here. Now u is given as capital U is equal to x minus y into x square plus 4xy plus y square. Now let's write down the formula as well. That's f of z is equal to integral dou u by dou x at x equal to z and y equal to 0 dz plus I, the minus sign, dou u by dou y into dz. This is also at x equal to z and y equal to 0. Alright, now find dou u by dou x first. Dou u by dou x is equal to this one, this into derivative of this. Okay, so x minus y into derivative of the second term, that is 2x plus 4y plus derivative of this, that is 1 into this x square plus 4xy plus y square. Now this is at x equal to z and y equal to 0. This gives us x equal to z means z term, here again z, so z into 2z, that is 2z square plus z square, the other terms get 0, so that is 3z squared. Now dou u by dou y is equal to this into derivative of this, so x minus y into derivative of the second term is x square goes, so 4x plus 2y plus this one minus 1 into derivative of minus 1 into x square plus 4xy plus y squared. So that is z 4z square minus this is again z square, that's again equal to 3z squared. Now applying to the formula what we get is integral 3z square dz minus I into integral 3z square dz. So this is z cube minus I times z cube. Now this is equal to capital F of z. Now we need small f of z, that's equal to capital F of z divided by 1 plus I. Okay, so this one can be written as f of z is equal to z cube minus I times z cube. So f of z divided by 1 plus I. So dividing by 1 plus I is not possible, so let's take z cube out. 1 minus I over here, 1 minus I divided by denominator 1 plus I. Just divide the numerator with 1 minus I and again 1 minus I over here. This gives us z cube into 1 minus I whole square, so that's a square minus 2ab, that is 2ai, plus b square is I square, so that is minus 1, divided by 1 plus I into 1 minus I, that is 1 square plus 1 square, that is 2. So 1 and minus 1 goes, so z cube into minus 2I divided by 2, so that's equal to I minus I z cube minus I z cube, that's equal to f of z.